Chapter 8, we're going to talk about hypothesis testing for population proportions. So hypothesis testing is used a lot when you talk about like medical experiments. We talked about experiments back in Chapter 1, where you have two groups. One group was your control group, and the other group might be your experimental group. And you might want to look like the death rate between the two groups, okay? And based on different medicines that you gave them. So what we can do is a hypothesis test to see if there's a significant difference between the death rates of these two groups. So we're going to talk about today is hypothesis testing for population proportions. Okay, so we're going to figure out how to set up a hypothesis test. When they talk about a p-value, what does that mean? Your significance levels, and what conditions are required for calculating a p-value and significance level. Okay, so how do you determine if someone is cheating when they toss a coin? So there's all kinds of theories out there, like if you have it heads up when you first go to toss it, it will actually be more likely to land heads. There's different things you can do to try to cheat when you toss a coin. Okay, so if the toss is fair, right, then your probability of heads should be 0.5. Okay? Otherwise, if they're cheating, it's going to be not 0.5. Okay? If they're cheating so heads will come up more often, then your proportion will be greater than 0.5. If they're cheating so tails will come up more often, then your proportion will be less than 0.5. So at this case, we're not sure which way the person might be cheating, so we're just say that your p does not equal 0.5. Okay, so if only 4 heads come up out of 20 tosses, is the person cheating? So if you notice down here, I have this number line from 0 to 20, right? Each one represents the number of heads you could actually get if you toss the coin, right? You could get no heads, and you'd say, well, that would rarely happen. Okay, that's what my null hypothesis here, which is what I'm saying. We think p is 0.5. If that's true, then you're rarely going to get no heads, or you're probably even rarely only get 4 heads. Somewhere in here is where things happens often. Okay, you would expect 10 heads, but you're not going to be that surprised if you get 8 or even 13 heads, but you would be surprised if you'd only get 2 heads if you were flipping a coin, a fair coin. So what we're going to do is figure out where should we draw our line to determine where something rarely happens, and we can notice it up here also, or where we're not really surprised. So where, at what value, my guess is most of you would say somewhere between 3, 4, 5, 6, somewhere in here is your breaking point between it rarely happening and saying it's not that unusual to happen. Okay, so we already talked about observations being unusual, and if you remember back to when we talked about z-scores, we talked about if a z-score was less than 2, if a z-score was greater than 2 or less than -2, then we would consider that unusual. So as we go through here, we're actually going to go back to talking about z-scores again, and we're kind of going to use that 2 and -2 idea to determine whether or not it's unusual or not. Okay, so what we write here is we say the null hypothesis, which we denote with an H, and this is a sub-0, or H naught, or the null hypothesis. That's what we believe to be true. Okay, so in this case with the coin flipping, if there's no cheating, no surprises, no effect, then that means my proportion, remember we use P for a population proportion, my proportion will be 0.5. Okay, then we have this alternative hypothesis, and this is what we hope or guess is true. So this is if we think the person is cheating, we think that P is not going to be 0.5. So the population proportion will not be 0.5. So we're going to take a sample, and in this case our sample would be just flipping the coin 20 times, okay, to see if what we end up with agrees with the null hypothesis or not. Okay. Now again, remember that we're testing for the population parameter, in this case P, the proportion, not the statistic. So what we're testing is the population proportion 0.5. We're not testing if our sample proportion is 0.5 or not. Because remember, our sample proportion is going to vary every time we do the experiment. So first we need to come up with an idea or hypothesis. So maybe we say Sally's a good guesser on true-false questions, or babies are born less often on Tuesdays. So once you do that, then we're going to write down the null hypothesis. So for our Sally question, our null hypothesis would be that the population proportion, or Sally's proportion of true-false questions that she would get correct, is 1/2. Because if she's just guessing on true-false questions, since there's only 2 choices, we would expect her to get about half of them correct. So the alternative hypothesis would be that Sally's proportion, again it's her population proportion, is greater than 1/2. The reason we're using greater than is because we're talking about her being a good guesser. If we say Sally's a bad guesser, then this we would have used less than 1/2. Okay. For the babies born less often on Tuesday, my null hypothesis would be that the population proportion is 1/7, the 1/7 coming from that there's 7 days in a week, so we would expect about 1/7 of the births to be on any one day. So since we're only looking at Tuesdays, we expect about 1/7 of the babies to be born on Tuesdays. And since we're saying babies are born less often, our alternative hypothesis would be that the population proportion is less than 1/7. Okay, so if Sally's a good guesser on true-false questions, right, then we would use our alternative hypothesis is that the population proportion is 0.5. The alternative hypothesis is that the population proportion is greater than 0.5. So how are we going to test this? We give Sally 100 true-false questions to answer. Okay, Sally's just going to guess. She doesn't know the answers to any of these questions. She's just going to guess, and we're going to see if she's a good guesser. Okay, so we're going to find Sally's proportion of questions she answered correctly. So let's just assume it's 65%. We're then going to calculate the probability that Sally could get 65% or more of the 100 questions correct, given that she should only get 50% correct. Okay, and then based on that probability, this is actually what we're going to end up calling our p-value eventually. Okay, so based on that probability, we're going to determine if Sally's a good guesser. Okay, so normally we're looking at if her probability that she could get 65% or more correct is less than 5%, we'd probably say she was a good guesser. Okay, because that's the it's not likely to happen very often idea. Okay, is it possible we might reject the null hypothesis and say that Sally is a good guesser when she really is not? That is very possible, because remember our cutoff point, if we make it about 5%, is 5% of the time we might actually be wrong in assuming that she was a good guesser when she really wasn't, if we did this over and over again. Okay, so that's what we call our level of significance. So the level of significance, which we denote with this Greek letter alpha, it's a lowercase alpha, is the probability of rejecting H0 or the null hypothesis when the null hypothesis is true. Okay, now this is something we don't want to do. That means we made a mistake. So the significance level should be small because we don't want to make the mistake of rejecting the null hypothesis when the null hypothesis is true. Okay, so this would be concluding that coin tossing is not fair when it was fair, or saying that the defendant is guilty but he did not commit the crime, okay, or concluding that the person has psychic abilities when she was just guessing, or also saying Sally is a good guesser when she really is not. Okay, so that's the probability of rejecting the null hypothesis when the null hypothesis is actually true. So since we don't want to do that, we want alpha, our level of significance, to be small. Okay, so since the level of significance is a probability of making an error, again, we want it to be small, so most typically we pick 5%. Now if you think back to our confidence intervals, that 5% kind of corresponds to our 95% confidence interval. Okay, so it's still within like 2 standard deviations of the mean idea that we're talking about usually when we do this. Okay, sometimes you need to make your alpha a lot smaller. Okay, or other times if it's not that big of a deal, that if you make that error, it's a lot larger. Okay, but a lot of medical experiments, when they do talk about testing being significant, most of the time they're going to use alpha of about 5%. Okay, so in conducting a hypothesis test, one takes a sample and then you just find p hat. Okay, so if you remember the central limit theorem for proportions, it says that the distribution of sample proportions is normally distributed, and its mean will be whatever the population mean is, and its standard deviation will be the square root of the population standard deviation times 1 minus the population standard deviation divided by n. Now you notice this has P0 here versus before I just always wrote it with a P. Okay, because what is P0? P0 is the proportion that's in your null hypothesis. Remember, for the null hypothesis we write H sub 0, that's the same 0 that's here. So when you use this formula, you're just putting in the p-value that was in the null hypothesis. So it's your population proportion from the null hypothesis. Okay, so the test statistic is the z-score for the sample proportion. Remember, your z-score is x minus your mean divided by your standard deviation. So in this case, it's going to be my sample proportion minus the population proportion, or the value that was in the null hypothesis, divided by the standard error, okay, which uses this formula right here. So you make sure you have a calculator handy when you do these problems. Okay, so the test statistics tells us how unlikely that sample proportion could have happened by random chance had the null hypothesis been true. Okay, so what we're doing is we're calculating the probability that we could be somewhere far away from what we think is true. Okay, so again, this goes back to if my test statistic is either greater than 2 or less than -2, it's unlikely to happen. It's more unusual. We'll get a little more scientific as we go through here and narrow that number down a little bit more when we do it. Okay, but for now, just think about how we determined if a value was unlikely before to happen. If the z-value was greater than 2 or less than -2, we kind of said it was unusual. Okay, so if the null hypothesis is true, then the test statistics will be close to 0. Okay, so therefore, the further the test statistic is from 0, the more the null hypothesis is discredited. Okay, so what we are looking to see if the test statistic is unusual. Remember, my test statistic is my z-value, right? And remember, if z-values are greater than 2 or less than -2, we kind of call those unusual. Okay, again, we're not necessarily going to be using the -2 and 2. I'm just trying to use that as an example so you remember exactly how this is working. Okay, so the p-value is a probability. Okay, so it's assuming the null hypothesis is true, because remember back in the test statistic, I said you take your sample proportion minus the population proportion that was in the null hypothesis. So we're assuming that it's true. Then the p-value is the probability that if the experiment were repeated, you would get a test statistic as extreme as or more extreme than the one you actually got. Okay, so think about your normal curve. You're looking at how far away from the mean are you when you go out, okay, and the probability that you could be out there. We're actually going to be using the normal table when we do this. Okay, so what's the probability that you could either be greater than or less than, that's what the extreme means, than the sample proportion that you actually got. Okay, so let's look at an example. So in 2010, 65% of online searches used Google as a search engine. So a hypothesis test was conducted to see if more online searches used Google in 2014. Of 300 randomly selected searches, 71% used Google, and the p-value was found to be 0.0147, okay, which is about 1.47%. So what we want to do is interpret this. Now, in this problem, we're not having to do any math. All I'm having to do is just interpret a p-value. Okay. So what this tells me is if the percent of online searches that use Google is 65%, then if another 300 searches were randomly selected, there is only a 1.47% chance that the number of searches that used Google would be 71% or more. So it's the probability that you could be this extreme, that 71%, okay, that extreme or more. So this looks like it's fairly unlikely to happen again. Okay. So since the p-value is small, the 1.47%, we would say that more online searches used Google in 2014 than in 2010. Because remember, we assumed it was 65%. We said, well, what's the chances of getting a sample proportion of 71%? And we decided it was about 1.5%, which is pretty small. So that means it must not be 65%. It must be something else. Okay, so hypothesis testing summary. First, you're going to hypothesize. Then you want to prepare, and you can read through each of these things on the slide. And a part of the preparing is checking your central limit theorem conditions. We talked about all this in Chapter 7, that the number of successes are n times p is greater than 10, and n times 1 minus p is greater than or equal to 10. Okay? And then you need to compute. That would be compute the test statistic, compute the p-value, and then interpret. Okay? So those are our 4 steps. And in the next over the next few sections, we'll actually talk more about how those 4 steps play and how you actually compute each of those 4 steps.